everybody. Welcome back to statistics. We are getting into our first inferential statistic. This is the one called chi-square. Now, there are two versions of chi-square that you're going to learn this week. And the first one we're going to cover is the one called the test of independence. So what we're going to do in this video is we're going to walk through the basics of how the chi-square works. Specifically, then, we'll cover the test of independence. And then the next video, we'll talk about hypothesis testing applied to chi-square test of independence. So let's go over some chi-square basics to get you familiar with it. So let's start with what is the chi-square. So some terms I want to introduce to you here are the terms parametric and non-parametric. So the key word in parametric, think the word parameter. A parameter is like a boundary, it's like a guideline. So when you have a statistical test that is parametric, it means that it is following certain parameters, or a better way to understand it is that a parametric statistical test follows certain assumptions about a sample and its distribution. A major assumption in a parametric test is that the sample is normally distributed. So in contrast, a non-parametric test is a statistical test that does not adhere to certain assumptions about the sample and its distribution. So a non-parametric test doesn't assume that the sample is normally distributed. This is useful because not all data is normally distributed, and so a non-parametric test can be used to analyze data that is not normally distributed. So the chi-square is a non-parametric test because it works with categorical data or frequency data, two terms that you've heard before at the beginning of the class. So since frequency data or categorical data isn't normally distributed because the data is not measured on a scale, right? It's discrete categories, separate groups, then it can't be analyzed using a parametric test. So it has to be analyzed using a non-parametric test. Chi-square is one of those kinds of tests. So chi-square is a non-parametric test. It examines frequency and nominal data, or just categorical data, simply put. Now, here's what the chi-square is really focusing on. It is testing to see if the frequencies, right, the amounts of data in each category that you actually gather, and the technical term here is the frequency data that you observe across your groups, is different from the frequencies that you may have expected to find. Let's say that you had 5 different categories and you expected a certain amount of data to fall in each of those categories. That would be your expectation. Then you go out and you gather your data and you find your observed frequencies, the amount that actually ended up in each category. And so the chi-square helps you to determine, is what you observed, what you actually gathered, what you found, is it different from what you expected to find? Now, like I said at the beginning, there are 2 types of chi-square tests. The one we're going to cover in this section is called the test of independence, and the one that you're going to cover after this chi-square is called the goodness of fit test. They follow the same assumptions. They're both non-parametric tests. They're both comparing observed to expected frequency data, but they're used in slightly different contexts, and that's the thing that I'm going to help to break down for you guys. So let's get into the basics of the test of independence and talk about how it works and how it is calculated. So I like to start teaching a new stat with focusing on the what and the when. What is the statistic and when would you use it? So what is the chi-square test of independence? Well, it is a statistical test that deals with 2 nominal variables, meaning that you're going to have 2 columns of data. If you picture a spreadsheet, you're going to have 2 things with data that you're going to be comparing. And what you want to see is if those 2 nominal variables, are they significantly related to each other or are they independent of each other? One thing I want to echo back to kind of tie this together with something you're already familiar with is if you remember back in the probability section, when we were looking at the table of data, especially when we were looking at what is the probability of something given something else, and we're looking at table of data with the totals and the grand total and all the combination numbers and all that. One of the things that I had mentioned there when we were talking about a joint probability and how we calculate it, the way you calculate a joint probability depends on whether you assume the two things that you're trying to see if, their joint probability, are they related to each other or are they independent of each other? And at the time I had just said, follow what the question says. If the question says they're independent, calculate it that way. If it doesn't say anything, then assume they're related, calculate it that way. But a question you could have asked in your mind at that time was, well, how do you know in reality if they're independent or related? A chi-square test of independence is a way, with nominal data at least, that you could determine if two things are related or independent of each other. So just wanted to tie that together with something you're familiar with. Maybe that'll help the concept sink in, help you remember it a little bit more. Now, when would you use a chi-square test of independence? Well, if you're working with nominal and categorical data, chi-square is going to be the type of statistic that you're going to use. Now, and especially if you have categorical data from one sample of people and you have data on at least two variables. And when you want to compare data you observed to data you expected, that's all chi-square. Now, how do you know when it's the chi-square test of independence? Again, if you have data on two variables. Goodness of fit test, just a foreshadow, only works with one variable. Test of independence works with two. So as we get into this, I like to always put this in the context of some kind of question. Remember, this is a statistics class about how stats are applied in the behavioral sciences. So the best way to learn stats, in my opinion, is to always think of them in the context of some real question that we would want to answer in the behavioral sciences. So take this hypothetical question. Are children's height related to children getting bullied? Let's say that you were to go on and become a great researcher statistician, right? My dreams and hopes are fulfilled in you. And you go get hired by one of a local school district or just a local school. And they ask you to look into what are the causes of bullying happening in that school. And so one of the things they're wondering is if kids are getting bullied based on their height. Kids are growing and some kids grow faster than others. You see height differences. Is that a basis, or is that connected to children getting bullied? So you're presented this question and you have to investigate, is the height of children related to children getting bullied or not? Now this question here, this scenario, this is our general question. So remember when we talked back in hypothesis testing, you have to start with a general question, but then you need to make it more technical. So we need to then specify our research question. Here's what the research question would look like. So when regarding a chi-square, remember we're looking at the difference between what we observed and what we expected. Okay. Now with a test of independence, you're specifically getting at, is there a relationship between your two variables or is there not? So is there a significant relationship between children's height and children getting bullied? Now here are the characteristics that indicate a chi-square test of independence is required. One, you're looking for a relationship. You're working with nominal data and you want to know if these two nominal variables of data are related. That's got to be the chi-square first, test of independence specifically. And of course, if you've got two categorical variables, you would also know it's a chi-square test of independence. Now, just looking at the variables of the question wouldn't tell you that. You would have to actually look at the data. And if the data was measured categorically, then you would know, okay, I probably got to use a chi-square. If you've got two nominal variables and you want to know if they're related, then it's got to be the test of independence. Now let's talk a little bit more about our variables. How do these variables work with a test of independence? Well, variables can take on whatever name that fits in the context of the data. We're just going to use X and Y to kind of label the two variables that we're working with. You won't ever have more than two variables for a chi-square, at least in this course. So you got X variable and a Y variable. We want to see if X and Y are related or are they independent from each other. So the best way to determine which variable is which is just pick whatever is mentioned first in the question. That's your X variable. It easily could be the Y variable, but I just want everybody to be on the same page. So whatever variable is mentioned first in the question, that is your X variable. So the X variable for this one is going to be children's height. And how is that measured? Well, you would look at the data to know how it's measured. Now, the data I'm going to show you in this example a little bit later, children's height is measured in just a binary category of short or not short. Not measuring in terms of height in inches, that would be an interval scale. Now, if we're measuring this categorically using a nominal scale, we just have short and not short. How many kids meet short and how many kids fit not short. Now, the second variable is going to be your y. So that would be children getting bullied. And again, it's got to be categorical. So we have a binary category here of just yes and no. Now, the categories of each variable could be more than two. Okay, but for the sake of this example, we're only going to be using just two for each variable just to keep it simple. So we've got short and not short for the x, children's height, children getting bullied is the y, yes or no. Now, here's what the data looks like. Let's say that you gather data from 209 kids in this school. So 92 of them fit the category of short, 117 not short, 72 say yes, they've been bullied, 137 say no, they've been bullied. And then you see those combinations there, short and yes, short and no, not short, yes, not short, no. So here's how the chi-square is calculated. Now I want you to bear in mind that the equation for the chi-square is the same for both chi-squares that you're going to learn, okay? So if you remember that symbol there, looks like a capital E, funny looking E, that is capital sigma. That means to sum everything that is to the right of it. So what are we summing? Well, what you'll do is you'll take, for each cell, for each combination, you're going to take the observed frequency minus the expected frequency. You're going to square that, you divide it by the expectancy, and you would do that for each combination. So with this data, we would do it a total of 4 times. So there's 4 combinations here. And then you would sum each of those together. So you should get 4 numbers, you sum them all together, and that is your chi-square. Now, what we need before we even get to doing the equation is we need to get our expected frequencies. And that's the equation that you see below the chi-square equation. That's E. Capital E is our expected. What did we expect to find in each category? Okay. So what you do is for each cell, you take that cell's row total times that cell's column total divided by the grand total, 209. So what you would use for the first one, let's just do the first one as an example. You would take, for short yes, you have, that would be, the row total would be 92 times the column total 72. And then you take that product and you divide it by 209, and then you should get your expected frequencies. Go ahead and pause the video, calculate all your expected frequencies, and then continue on, and you'll see if you got them right or not. So here's the expected frequencies you should have gotten, okay? So this is what you would expect to find. And the assumption is what you would expect to find, assuming that they are not related. Okay? So remember, it's kind of based on the idea of the null hypothesis. So what would you expect to find, considering the totals, assuming they're not related? You would expect to find around 31 kids in the short yes, 60 in short no, 40 not short yes, 76 and not short and no. So now we have our expected frequencies, and we want to compare them to our observed. You can kind of see here that they're a little bit different, right? But are they different enough to where we would say that, assuming they're independent, we would expect to find the differences here? Or is this too unlikely? Was it too unlikely for us to find these differences, assuming height and bullying are independent of each other? So here's what we're going to do. You're going to fill in this table for each row, take the difference between the O and the E, square it, and then divide it by E. And then at the very end, you're going to do that for each row, and then you'll add up all 4 numbers to get your chi-square. So go ahead and pause the video, do those calculations, and then continue on. So here's what you should have gotten. So you can check your numbers there, see if you want on the right track. And ultimately, you should have gotten a chi-square of 9.11. Okay. Now, what does that number mean? How do we interpret the 9.11? Okay, chi-square score of 9.11. What is that telling us, right? So a chi-square score represents the statistical relationship between your observed values and their expected values, okay? The further the chi-square is from 0, the more different O is from E. That's kind of what it's telling you. If the chi-square score was 0, it means your observed values were exactly the same as your expected values, which would indicate that they are that your 2 things are probably independent of each other. Okay, if what you found is connected to what you saw, but that's in the context of the test of independence. So let's just speak broadly here, because what I'm saying here applies to the goodness of fit test as well. So a larger chi-square score, one that's further from zero, it indicates that O and E are more different from each other. Now, what would account for O and E being more different from each other? Why would you end up with a larger chi-square score? A possibility with the test of independence is that the two variables may actually be related, which is why your observed values are different from the expected. Remember, the expected values are calculated on the assumption the two variables are independent of each other. So if they are actually related, that is why what you found is so different from what you expected to find, because what you expected to find was based on them being independent. If they really were independent, you should have found what you expected. But since you didn't find what you expected, since your observed was so different from the expected, maybe that's because the variables are related. So that's giving further insight into the case there. So to put it in the context of our scenario, a relationship between children's height and being bullied may account for a larger chi-square score. 9.11 is pretty far from zero in this case. So maybe it's because the height of a child is related to whether or not they get bullied. So again, a larger difference, a larger chi-square score could also be due to sampling error, okay? So it could be a bad sample of children. So that's another thing you want to keep in mind here with that. It can be because of relationship or it could be because of sampling error, okay? What in the next video, what we're going to get to is now wrapping up our scenario and actually completing hypothesis testing using the chi-square test of independence.